Good afternoon, everyone. My name is Haichuan Chu. You can also call me Ken. I'm a PhD candidate at Georgia Tech, and I'm advised by Professor Brendan Saltaformaggio and Professor Jeman Park. So I'm very happy to present Diva, extracting victims and abuse vectors from Android accessibility malware. So Android's accessibility service, known as the Ally service, it is designed to enhance the usability of users. And they achieve this by providing alternative input or alternative outputs, such as reading the screens. And common usage of this benign Ally utility include text-to-speech, voice control, and gesture recognitions. So to achieve these functionalities, the Ally service stands as an exception to Android's app-isolated sandbox design, in the sense that it allows apps to control the GUI screens of other applications. And given this powerful capability, it has always been widely abused by attackers to attack the device via the GUI. And common abuse techniques include eavesdropping the user's screens and conducting automated GUI actions without the user's consent. And Ally malware, they usually target other applications, perform victim app manipulations, and make themselves harder to remove by adopting those Ally-based persistence mechanisms. So let's see a real Ally malware in action, stealing money from users' mobile banking accounts. As you can see on the top of the screen is the pig stealer Ally malware impersonating as a cashback amp of a Brazilian banking app called PagBank. As you can see in the middle of the screen is the legitimate banking app. And when the user opens the malware shows a phishing screen saying grant accessibility permission to get cashback. And when the user clicks continue and then clicks OK to grant that permission, the malware will send a notification saying open PagBank for synchronization. And the user happily does that by clicking the real banking application. And after he does that, the malware will use accessibility to automatically click that show balance button to know exactly how much balance is in the user's account. And after it knows the balance, it will show a fake overlay screen, and under that screen, it will use Ally to click the initiate transaction button, enter the attacker's account number, enter the available balance, and click send money to transfer all that money away to the attacker's account. So for Android malware, Google Play Protect is responsible for mitigating Android malware. And for an ideal mitigation of Android Ally malware, we would expect the Google Play Store, whenever they detect a Ally malware, to first let us know what are the victim targets. And this is to notify the users that what the malware is targeting so that they can go ahead and secure their other assets. We would also expect them to output the malware's abuse vectors and use that to notify the app developers so that they know exactly how they're being targeted by malware and they can go ahead and deploy tailored defenses. And finally, we expect them to output the persistence mechanisms the malware adopts so that it can be used to notify Android OS developers and block future illegal actions. However, getting all those three information is actually very challenging because Ally malware usually adopt encoded victim app searches, for example, one-way hash functions, which makes it impossible to decode without a correct victim environment. They also usually adopt dynamic code loading techniques so that the abuse code that you try to analyze may not even be there at the start of the analysis. And they also adopt trigger-based execution so that the extractions of persistent mechanisms might be incomplete. However, we found in our research that Ally abuse is actually a double-edged sword. The malware's usage of Ally APIs actually solves our three challenges. Since the malware has to eavesdrop on the victim applications before conducting their abuse actions, we can simulate the victim app actions and use that to review the targeted victim apps. And since they also need to conduct their GUI actions based on Ally APIs, we can conduct symbolic analysis to model their abuse behaviors. And finally, since they all try to disrupt the device control via the GUI, we can apply the triggers to those device control screens and intercept the malware's behaviors to infer their persistence mechanisms. So to help Google Play Protect mitigate Android malware, we designed Diva, the detector of victim-specific Ally abuse. When the Google Play Protect detects an Ally malware, it will send the Ally malware together with the device applications to the backend. And Diva, acting as a cloud-based solution, will first run the malware through its victim-guided sandbox, which will output the malware's victim targets. Then it will run symbolic analysis to output its abuse vectors, and finally run the malware through the ally trigger and interception sandbox to gather its persistence mechanisms. So the first key component of Diva is its victim-guided sandbox. So our insight that ally malware will monitor the victim apps before loading and executing abuse code. So that's why we apply dynamic hooks to victim query APIs, in this case, to return real victim app parameters to the malware. For example, get installed applications. And these parameters are collected in a victim parameter database consisting of 37K real victim app static parameters, such as their package names, their launch intents, etc. And after that, Diva monitors the malware's code loading by hooking the class loaders. And Diva outputs a victim if the malware load code after verifying that certain victims are present and valid. So for example, in the video demo case, we say the pig stealer malware targets PegBank because it scans for PegBank and loads PegBank's specific abuse code. And our second insight is that ally malware queries victim app GUI state before conducting tailored abuse actions. So Diva actively broadcasts victim ally events, in this case, Windows state change events, to mimic the victim app's initiations. Then Diva monitors the malware's GUI actions responses to those events. And finally, it outputs the victim app if we see it conducts GUI actions after seeing the ally events. So for the pig stealer malware, we say it targets PegBank because it uses ally to click the show balance button after the PegBank starts. The second component of Diva is its abuse vector-guided symbolic analysis. We first collected the model API sequences and data flows of real-world malware abuse vectors. For example, in the first row, the automatic transaction means the malware can automatically use ally to inject clicks or filling texts. And stealing credentials means the malware can log the screens and eavesdrop users' text inputs. So to confirm the API sequence and data flow, we use symbolic analysis and record their execution constraints of each pass. And then we use the solved execution constraint to attribute those abuse vectors to the victims. And finally, Diva outputs a victim-specific abuse vector report. For example, in the pig stealer case, we say it targets PegBank by conducting automated transaction and stealing the user's credentials. And the final component of Diva is its ally trigger and interception sandbox. So Diva first models the triggers and behaviors of real-world ally persistence mechanisms. For example, we say the malware can disable the device protections, meaning it can use ally to automatically turn off the Google Play Protect in the device settings. And we say the malware prevent information lookup or uninstallation means it can use ally to return home or return back to navigate the user away from the screen whenever it detects the user is in malware's app information screen. So Diva does is first apply the triggers by sending intents to navigate to the persistence mechanism's trigger screens. And then Diva captures its ally behaviors by intercepting the malware's ally actions, such as pressing the back button or returning to home. And finally, Diva outputs the persistence mechanisms if both the trigger and the ally behaviors are present. So the pig stealer case, we say it persists by preventing users from revoking its granted ally permission. So for the large-scale evaluation of Diva, we collected a dataset consisting of 9,850 ally malware, spanning across 197 malware families. And the victim app database consists 37K real victim apps. And this is done in collaboration with our collaborator Netscope, which is a cloud security solutions company aims to identify and mitigate malware threats. They also seek to fortify their defenses against mobile malware attacks. So we run Diva with an average runtime of 110 seconds with no front-end overhead on the user's device. And we have some very interesting findings. We found that the most abused vectors by malware are stealing credentials and conducting automatic transactions across all categories of victim apps. We found that 83% of ally malware target banking apps, And 70% of ally malware target authentication apps. 74% of victims are banking applications, and 7% are cryptocurrency applications. Diva also extracted 7 categories of ally-enabled persistence mechanisms. So 92% of malware prevent the users from uninstalling the malware or revoking the ally permission. Diva also observed some more intrusive behaviors, but they are actually less observed. For example, only 19% of malware prevent users from powering off their device or restarting their device, and only 2% of malware escalate to admin privilege using ally. And there is much more in the paper, including a detailed 2-factor authentication stealer malware analysis, a detailed ally ransomware analysis, discussion about victim app developers' proactive defenses, and more highlights. Thank you, and I'm open to any questions.